supposed to happen. That wasn't you, it's okay.
Go ahead and start the ISL Colloquium, I think is the current formal name. And today we have Venkat Chandrasekaran from Caltech. That was by way of Berkeley, thus the Michael Jordan connection. And that was by way of MIT, which was the Alan Wilson connection, I guess, right?
Wilson and Berkeley.
Okay. So, it's going to be computational and statistical trade-offs and via convex relaxation.
Great. Thanks for the introduction. Thanks for the invitation. Great to be here again. Joint work, as Stephen mentioned, with Mike Jordan at Berkeley. And it's about a class of problems in statistical inference where ideas from convex optimization, specifically convex relaxation, have a very interesting role to play. But the class of problems that I care about are sort of more, folks use the term big data, massive data to refer to this. But really it's an issue of problems involving time-constrained inference. The idea that you wish to make inferences or decisions within a fixed time budget, a fixed amount of time. And this fixed amount of time is usually quite small. So you can imagine these sorts of ad options, right? Someone surfing the web, you go to Google or a cricket website or something, right? Do a search, and based on some cookies collecting user information about you, there's an auction that runs up in the cloud to decide which ads are shown to you. And this decision, this whole process, needs to be made on the order of a millisecond, or maybe less. Right? And so you have very fixed and very harsh time constraints, and you want to make informed, reasoned decisions within this time budget. But this sort of conflicts with classical thinking or classical analysis in statistics. Traditionally, the viewpoint in statistics was that the amount of data somehow is the bottleneck. And I'm going to look at what are the best kinds of estimators that I can produce that operate given a fixed amount of data. Best given some error. So what's the best estimator or best decision-making procedure given a fixed amount of data? And this is, this goes by the term minimax analysis or several other types. Time is really not a key constraint in this sort of traditional thinking in statistics. So when I talk about the best estimator given a certain amount of data, or the best decision-making procedure, I talk about best with respect to an error metric, but independent somehow of time. But more recently, in applications like the one I just mentioned, data is typically plentiful. These ad auctions that I mentioned are an example. High-frequency trading in finance is another example, where data is plentiful and time is really the key bottleneck. And so we really need a theory of estimation or inference that incorporates time constraints. What are the best estimators given a ton of data, but a limited amount of time, and budget sometimes? Okay? So how do we think about this? And the way I'll think about this is as follows. So I've just cooked up a few numbers here to just suggest a simple thought experiment. So consider a typical inference problem, and by inference I mean just a parameter estimation problem. And suppose you have n equals 5,000 samples to estimate your parameter, or to solve your inference problem. And you run your computer for an hour, and you obtain a risk, or statistical accuracy, of 0.03. So you chug your computer along for an hour, process these 5,000 samples, and that's the error that you get. Now suppose I give you 500,000 samples, 500,000 data points. You're able to obtain a much smaller risk, much better accuracy, but you need to run your computer for 20 days. Right? More data, better accuracy, but more time. This is sort of the traditional way of thinking in statistics. But suppose I tell you that I'm happy with a risk of 0.03, so an accuracy of 0.03, but I give you 500,000 data points. Why might this actually be a reasonable thing to assume, by the way, before we go further? this might be a reasonable thing to say because we maybe don't care about small improvements in risk lengths. 0.03 is good enough accuracy. We might say this is okay because statistical models are just approximations to reality. They're not reality, right? And so getting very, very fine accuracies don't make sense. So getting to an accuracy of 0.03 with my statistical model may actually be good enough. So if I'm happy with that kind of risk, but I've given this amount of data, what should your response be? One response should be that, imagine the data is IID or exchangeable, right? So 500,000 is, a lot more than 5,000. One response is to just take a 5,000 large subset of this 500,000 large data set, run your computer for an hour, and get to a risk of 0.03. So that line of thinking suggests that you should never require more than an hour on your computer, right? If you live in this setting. But can you potentially exploit the extra data that you have to reduce computation? Can you say if I have 10,000 data points, I need just half an hour to get to a risk of 0.03. If I have 100,000 data points, I need just 5 minutes to get to a risk of 0.03. And if I have 500,000 data points, maybe I need 1 second to get to a risk of 0.03. Certainly, runtime should not increase if I keep my desired risk fixed. Right? As I get more and more data, runtime should never increase. But can we potentially get it to decrease? Right? And this, I claim, is sort of, it hints at a tension, in my view, at the intersection of computer science and statistics. So the traditional thinking, again, just to reiterate, in statistics, is to characterize trade-offs between amount of data and error. More data, smaller error, and what is the rate at which this error approaches zero as I get more and more data. Right? This is the traditional classical thinking in estimation theory, in minimax analysis, so on and so forth. The thinking in computer science, or in numerical computation, is if I run my algorithm for more and more iterations, at what rate does the error decay to zero? So how does the error go to zero as the function of, say, the number of iterations, or the amount of work that I do? Right? So we characterize trade-offs in that space, in that plane. But we don't really think of data as a resource in computer science, right? Time is a resource in computer science. More time is always good for me. More space is always good for me. But we don't think of more data as a resource, or data as a resource, so that more of the resource is actually good for me rather than bad for me. We say 1 gigabyte, I can run my algorithm. 100 gigabytes, I can still do it. 1 terabyte, I fail, right? And that should never be the case if the desired accuracy is fixed. If I don't care about improving my accuracy as I get more and more data. And so what we really aim for in this talk is to try and understand this plane, that axis, between runtime and amount of data. How can we talk about trade-offs along those lines? Okay? So even before I go to specific concrete problems, I'll talk at a conceptual level based on sort of the state of the art in statistics and computer science, about what we can possibly expect in trying to study time-data trade-offs. What are the limits of what we can expect in trying to understand these two axes jointly? And then I'll talk about a simple statistical inference problem for concreteness, and talk about convex programming-based estimation procedures for this class of inference problems, and how the idea of convex relaxation, once you build in convex programming-based estimators, how the idea of convex relaxation can actually provide a mechanism to obtain trade-offs between amount of data and runtime. All right. So the way I'm going to think about time-data trade-offs is as follows. So runtime is going to be one axis, number of samples, n is going to be another axis. Like I said, I'm going to fix the desired risk. So fix the risk. And I'm going to view inference procedures or algorithms as points in this plot. So these are 3 procedures, and this requires runtime that much and number of samples of that much to get to my fixed risk. And the idea, or the hope, is that we should see plots that look like this, right? As I get more and more data, runtime actually goes down. Anytime you wish to understand trade-offs between 2 quantities, the first question you have to ask is, what do horizontal lines mean and what do vertical lines mean? Right? So what does a vertical line mean in this axis, in this 2D plot? A vertical line says, to get to this fixed risk, I'm going to give you an unbounded amount of time, no constraints in time. What's the minimum number of samples you need to get to your fixed risk in your inference problem? And this is, like I mentioned, very much the area of study or area of investigation of classical estimation theory, minimax analysis, and so on. And this is relatively well understood in many cases. There are still interesting problems in this domain, but it's a very rich literature and very well understood in many, many cases. We can now ask, what does a horizontal line mean in this plot? And what it's saying is, I'm going to give you an unbounded amount of data now. What's the smallest number of operations you need to perform to get to your fixed risk? What's a non-trivial lower bound, an informative non-trivial lower bound on the number of operations? And this is much, much harder. I mean, some of the hardest problems in complexity in computer science, we don't have interesting informative lower bounds for. The satisfiability problem, which many of you may be familiar with. The best known algorithms that we know of require runtime that's exponential in the input size. The best lower bounds that we're able to prove are linear in input size. So we don't even have super linear lower bounds. That's a big open question in complexity theory. And so this very much is poorly understood, depends on the kind of computational model, depends on the kind of infrastructure you have computationally, and so on and so forth. So this will very much inform the limits to which we'll be able to push any attempt to try to understand time-data trade-offs jointly. Right? We don't understand lower bounds in time, so trying to understand these trade-offs jointly, there are going to be certain limits to what we'll be able to do. And so the way we'll think about things, there are things you can say conceptually just at a very high level. The idea is, as I go from that amount of data to that amount of data, it's an increase in data. If I use the same procedure with this amount of data, if I use algorithm A with this amount of data, you should expect runtime to increase, right? So what you need as you get more and more data is some mechanism to back off the simpler algorithms. You need some mechanism to be able to process larger data sets more coarsely, with the idea that aggregated over the inferential power of a larger data set, you still get to the same accuracy. That's one conceptual idea. A second very basic point you can make is that if I give you 1 trillion data points, and if there is a computational cost associated with touching every single data point, then it makes sense at some point to just throw data away. Right? And so you should expect to see floors like this. And the precise point at which the floor occurs depends on your computational infrastructure, the kinds of algorithms you use, so on and so forth. But you should expect to see something like this. Right? And the last thing, motivated by what I just said in the previous slide about complexity theory lower bounds, is that when I talk about trade-offs, I'm going to talk about trade-offs in the following sense. If you give me more data, I'll produce a weaker algorithm that has a smaller upper bound on runtime. So typically when we think about trade-offs, you can talk about Heisenberg's uncertainty principle, right? Change in momentum times change in velocity bigger than something. So those are all lower bounds, typically. I'm not going to be producing lower bounds jointly on time and amount of data, because producing lower bounds just on time is hard enough. So as you give me more data, I'll produce different algorithms that have smaller runtime upper bounds. Okay? So that's the sense in which I'll be talking about trade-offs. Question?
No, maybe a comment.
Okay.
So we already know what the point A is, right? So if this is the vertical line, it corresponds to when you don't have any limits on the runtime and a certain point.
Could be. I mean, I wasn't imagining A being at the leftmost point here, but yes.
No, of course, but this corresponds to the first algorithm.
Yeah, the algorithm that perhaps operates with the smallest amount of data. Yeah, you could think of A if you wished like that. But as I give you more and more data beyond that point, yeah, you should hope to see it. Okay, so now let's be more concrete. Let's focus on the specific estimation problem. And I'm going to, all of what I said is somehow you imagine generally and abstractly applicable. So we wanted to come up with the simplest possible problem where you could still talk about these things in an interesting way. And I don't think there's anything too much simpler than this. And so we have just a simple denoising problem where the signal x star belongs to some signal set S living in p-dimensional space. The noise is Gaussian, standard deviation sigma. And I observe n IID samples yi drawn from the y. Okay? So each of these yi's also lives in p-dimensional space. The signal set S is known to me, but the specific point x star, of course, is not known. And x star is what I wish to estimate. Now, the sample mean is clearly a sufficient statistic here. And so a natural estimator might be to say, okay, I'm going to search over all x's, find the closest one to the sample mean that still lives in my signal set S, right? So project the sample mean, if you will, to the signal set S. Now, frequently, the kinds of signal sets that we care about are difficult to project onto. And some of the examples that I'll talk about, these may be combinatorially complex in terms of the number of points in the signal set, or maybe in other ways very, very complex to project on. And so a natural thing to do, and this is a philosophy that we've seen in a lot of papers over the last 2 decades or so, is to consider convex relaxations, convex programming-based estimators. So to say that I'm not going to project the sample mean onto S, but rather onto some convex set C, such that S is contained inside of C. And depending on how complex C is, these projections can be less or more attractive. And this idea actually has a long history in statistics. This whole idea of shrinkage estimation, projection onto convex sets-based estimation. Convexity is useful both for analytical reasons, but also for reasons of tractability, computation tractability. There are many interesting surprises in high dimensions, the setting where P, the signal dimension, is very large. And there have been lots of interesting work. It's an active area of research recently to look at different kinds of sets to project on. So you can use the L1 ball, the trace norm ball, and so on and so forth. Very, very active area. But in any case, to understand what the statistical performance is of this estimator, we need two definitions, just 2 pieces of math. The first is, both are ideas from convex geometry. The first is what's called the cone of feasible directions. So given a convex set C and a point x star in the convex set, the cone of feasible directions is defined as the set of directions that I can move from x star into C. Okay. So if that's my signal set, think of this as some complicated kind of signal set. This is a convex set that contains S inside of it. The set of directions that I can move from x star into C is all these directions. Okay? So that's a cone of feasible direction. The second definition is something you see both in machine learning as well as in convex geometry in different forms. So it's called the Gaussian complexity. I put a square here because there's a square here. Typically it appears without the square. But in this talk we need the square. And it's defined as follows. I'm going to specifically define it just for a cone T. So the Gaussian complexity of a cone T is the expectation, but before looking at the expectation, it's the worst case inner product, the supremum over all these guys, of Z, over all guys in my cone suitably normalized. So the cone is obviously something that sort of goes off to infinity, and so I need to suitably normalize things. Okay? And so I take the supremum of the worst case inner product for a Z over all guys in the cone that's suitably normalized, take the square. And the expectation is with respect to Z. And Z is the same noise that I had before, right? So here, Z would be Gaussian, and so that's why it's called Gaussian. Okay. So we have cones of feasible directions into convex sets. And we have Gaussian complexity, some measure of the fatness of a cone. One thing I'd like to point out is that if a cone is larger, as a cone gets larger and larger, this Gaussian complexity stuff gets bigger and bigger, right? The Gaussian complexity. Okay. So now, given these two definitions, the risk of this estimator, so this is an estimator that takes an n samples and uses C as the constraint set, is given as follows. So the expectation, the mean squared error is bounded as sigma squared over n, the natural quantity that you expect to show up, times the Gaussian complexity of this column, of the cone of feasible directions from X star into C. X star belongs to S, the signal set. The signal set is contained inside of C. So it makes sense to talk about the set of feasible directions from X star into C. And this is what you get. So if the cone is smaller, this Gaussian complexity is smaller, and I have a tighter error. Yeah, question?
Can you give some examples of Gaussian complexity for natural classes like the?
Yeah, that I'll actually it will come up in the later on. The proof just involves applying the optimality conditions of the convex program that I wrote down. And the intuition basically says, okay, the only errors that I can make as I move away from X star are directions that take me from X star into the convex set, because that's a constraint that I have, right? Directions that take me from X star outside of the convex set don't actually matter. And so I only consider errors in this cone of feasible directions. So for instance, if I don't really constrain, I don't use any reasonable constraint, I just say all of RP. So I'm just taking the sample mean as my estimate in that optimization problem. This mean squared error is sigma squared divided by n times p, which is exactly what you should expect to see. You can generalize this proposition in several ways, and I can talk about it. But okay, the point I wish to make is this. This is again the proposition written. If I wish to obtain a risk of at most 1, remember, going back to the beginning of the talk, we said we wish to fix the desired risk, right? The desired accuracy. If I fix that risk to be at most 1, so I'd like this to be at most 1. One way to get to that is to say that n, if I just shuffle things around, should be larger than this stuff, right? N should be larger than sigma squared times the Gaussian complexity of this column. Yeah?
For this bound to apply, does C have to be a superset of S?
Yeah. I mean, there are ways to sort of improve upon that, and that's what this was about, but yeah. Yeah, that's it. At least the sense in which I'm talking about it. Okay, so now, what does this say? If I have, so two observations. Observation number 1 is that this Gaussian complexity term is monotonic in C. The larger C is, the larger the set of directions from X star into C, so the larger the cone of feasible directions, and consequently the larger the Gaussian complexity of that cone. So what this means is, if I have a very large number n of data samples, I can use a very large convex set so long as this times sigma squared is still less than or equal to n, right? Because all I care about at the end is getting a risk 1 estimate. And as long as this times sigma squared is less than or equal to my very large n, I'm okay. And this shows the same thing basically in pictures, as I use a weaker convex set than C, a set C prime, and has a larger cone of feasible directions from X star, and a smaller. So if I can now show for you that a larger convex set C prime than C is easier to project onto computationally, then I'm done, right? This whole business of time-data trade-offs basically relies on saying that larger convex sets, or certain kinds of larger convex sets, are easier to project onto than smaller convex sets. And so this is what the algorithm weakening mechanism will be about, using larger sets to project onto. And this is one of the big lessons from the optimization literature over the last 10 to 15 years and beyond, where if the signal set S is suitably structured, I'm not going to go into the details there, then one can obtain very interesting families of outer approximations to the convex hull of S. And this family of approximations is ordered in two very interesting ways. It's ordered in approximation quality, so these sets are nested inside each other. But it's also ordered by computational complexity, so that C1 is easier to project onto than C2 is easier to project onto than C3, and so on and so forth. So it's in general not the case that a larger convex set is easier to project onto than a smaller one, but these specially constructed hierarchies have this property. These are hierarchies of approximations. Depending on the kinds of hierarchies you consider, you might consider polyhedral hierarchies. So these are hierarchies of polyhedral approximations to your convex set. You can consider hierarchies of semi-definite relaxations to your convex set. And there are many, many other families of relaxations. And the manner in which these relaxations are constructed is based on an idea called lift and project that I very briefly want to tell you about, because it's a very cool idea for convex optimization and convex geometry. So the way we think about representing convex sets or writing convex sets in a computer, so we can actually optimize over these sets, is to represent these sets as the projection of some set upstairs, as the projection of a set in a larger dimensional space. So we typically represent C as the projection of a section of a cone that lives in some higher dimensional space. Okay? And the larger the dimension in which this cone lives, the better will be my quality of approximation, but the more will be the computational cost that I have to pay, because I have to do computations in this much, much larger dimensional space. And so these are sections of these cones. If the cone that I use is the ortho, then I end up constructing linear programming-based relaxations. If the cone that I use is the PSD cone, the cone of positive semi-definite matrices, then you get semi-definite programming relaxations. And there are very principled ways to construct these sorts of hierarchies given sets S that have interesting structure. I'm happy to talk about this more offline, but this is beautiful work in the optimization literature, work by several folks. Okay. So I wish to do, very briefly contrast to previous work that attempted to understand these sorts of time data trade-offs. There was a lot of work, especially, I guess, folks in machine learning are interested in learning classifiers. And their work mainly focused on SVMs and variants of SVM. And at least the idea, there's a ton of work in this area going back even the late 90s. But a central sort of point of departure between what they do and what we do, they're looking at slightly different problems. Of course, we are looking at denoising problems. They looked at classifier learning. But the idea there is that a lot of extra data is required to be able to back off a really simple algorithm. Whereas something that we'll see in the examples that I'll present later is that just a modest amount of extra data is required, in these denoising problems at least, using convex relaxation, to be able to back off to very simple algorithms. There's also work by Arash Amini and Martin Wainwright, and R.T. Singh's group at CMU on sparse PCA and time data trade-offs in these contexts, and others as well. But a general, I think, point of contrast to all these previous ideas is that I think we focus on algorithm weakening as a central mechanism. And I think it is essential that if you wish to realize any kind of time data trade-off, you need a notion of algorithm weakening. You need to be able to say, as I get more data, I need some mechanism to be able to back off the simpler algorithms, to process larger data sets more coarsely. And the thesis of the talk is that convex relaxation is a very principled and very general way to do this, as you'll see in some of the examples that I'll talk about in the next few slides. And so before we get to these examples, there are a couple of things I really wish to point out quickly. How do we calculate runtime? There are two things required in these runtime computations, right? The first is the number of operations to compute the sample mean. So remember, I had n samples, I computed the sample mean, and then I project that sample mean onto a convex set. So that's the number of operations to compute the sample mean, and then I have some number of operations for projecting onto some convex set. This quantity actually increases as I get more data, right? As I get more data to compute the sample mean, as n grows larger, this stuff increases. But the hope, and as you will see in the coming slides, what is true in many examples, is that that increase is offset by an even larger decrease in the number of operations required for projection onto the convex. Okay? And so this is how we'll realize a time data trade. The second thing is to estimate Gaussian complexity, and this perhaps relates to the question that was asked. I'll provide concrete estimates in the next few examples, but this is a general proposition that we use in all of these examples. So there's a general technique you can use, which folks in machine learning especially prefer, based on covering numbers. If you can cover your cone well, if you can compute these covering numbers well, there's a general formula to do Dudley that lets you compute these Gaussian complexities. But because of its generality, and it's very powerful, but it's also very general, and because of that, it's usually not shown. If you specifically care about Gaussian complexities of cones, of convex cones, then you can do something very interesting and something much shorter. If your cone P has a dual is again a convex geometric concept, where the dual has relative volume mu. So the dual covers a fraction mu of the space. So mu is a number between 0 and 1. Then the Gaussian complexity of your cone is rounded as follows. Let's do a basic sanity check. If you have a fatter cone, you expect Gaussian complexity to get bigger, right? So if I have a fatter cone P, its dual becomes narrower, its dual becomes smaller. So mu becomes smaller, and 1 over mu becomes larger, and it all makes sense, right? So at least at that level it makes sense. Now the proof of this appeals to Gaussian isoperimetry. What that basically says is rather than looking at all convex cones where the dual has relative volume mu, you only need to look at the spherical cone with dual having relative volume mu. Because you care about Gaussian complexity, the spherical cone is in a sense the extremal one. And so you just up about the Gaussian complexity of all these cones by the Gaussian complexity of the spherical one with dual having relative volume mu. And then you just do a whole bunch of algebra with the spherical cone. And you get to this number. Alright, so some examples now. The first example is where the signal set consists of what are called cut matrices. These are outer products of signed vectors. So these are matrices of the form AA transpose, where A consists of just plus minus ones in its entities. Okay. I'm assuming, by the way, that S lives in p-dimensional space. So A lives in square root p-dimensional space, whatever that is. Okay. These sorts of signal sets are of interest, if you care about collaborative filtering, clustering, and related problems. What's the best possible convex set that you could write down in constructing these estimators? The best one is just the convex hull of S, right? That's what's called the cut polytope. If in fact you could project onto the cut polytope, the number of samples that you would require to produce an estimate with risk 1, remember, we always desire a risk of 1, and that's what's going to be fixed. We fix the desired accuracy. The number of samples you need is some constant times square root p. S again lives in p-dimensional space. The number of samples you need is a constant times square root. And this is obtained by applying that theorem about Gaussian complexities that I just discussed. But projecting onto the cut polytope is very hard, because the cut polytope is a convex set. It's intractable as far as we know to project onto. If we could project onto it tractably, we'd be able to solve max cut and related problems tractably. A relaxation of the cut polytope that's considered in the combinatorial optimization literature, the famous SDP-based relaxation, is what's called the elliptope, semi-definite relaxation. The number of samples required to produce a risk-1 estimate if you could project onto the elliptope is a larger constant, provably a larger constant times square root p. But to project onto this set requires a speed of the 2.25 operation. The reason you get the strange exponent is because I'm thinking of my matrices as living in p-dimensional space. So it's not k by k dimensional space or something like this. That's why you have these strange looking exponents. But I wish to keep the parameter space to be p always. An even weaker relaxation than the elliptope
So are you saying that's k to the 4.5? And
Yes,
k
that would be k to the 4.5. Yes, exactly. Yeah, absolutely. An even weaker relaxation, the cut polytope, is the nuclear norm ball, suitably scaled. This is the convex hull of rank 1 matrices. If you look at your signal set S, it consists of rank 1 matrices. To project onto this requires just doing an SVD. And a risk 1 estimate in this case requires a larger constant M squared. Yeah.
So previously you said that what matters is the size of the cone, the number of the cone of directions you can move from X star to stay
Yeah.
set, right? So does that somehow hinge on, to get gains, do you require X star to kind of be at the boundary?
Yeah, so if X star, so, you know, that proposition can be improved in several ways. If X star has, you know, I can move in all directions from X star, but there is a point near X star that has a very narrow cone, then I just have an extra payoff that depends on the distance between X star and this point with the narrow cone. And so I pay that extra point and then I compute the Gaussian complexity from this point with the narrow cone. So you can do things like that. And those are ways in which you can improve and tighten that proposition. There's one flavor for this. Another result, I think this is an example motivated by an interesting class of problems involving banding estimators for covariance matrices. So work by Peter Bickel and his student Lisa Lavina several years ago suggested that a good way to estimate covariance matrices is to band them. If you have some sense that the underlying random variables are ordered so that correlations between faraway variables and case variables, a good way to estimate these covariance matrices is to band them. Take the sample covariance, taper or threshold things a certain distance away from the diagonal, and so on and so forth. Now, if you didn't know a good ordering for the variables, then what you'd like to do is simultaneously learn an ordering where the covariance decays rapidly away from the diagonal, and then do this banding-based estimation. Right? So a problem motivated by this conceptual idea of doing joint variable ordering as well as covariance estimation is the following. So I'm going to let M be a known tridiagonal matrix. So a very nice banded matrix. Tridiagonal meaning diagonal, one away from the diagonal and 0 is everywhere else. It's a covariance matrix. Think of M as being a covariance matrix, if you will. Needn't be necessary. And the signal set S is all possible shufflings of the rows and columns of it. Okay? All matrices constructed by shuffling the rows and columns. So pi is a permutation. Now, again, the best possible, so M is known, this is a stylized problem. The best possible convex set that you could write down is the convex hull of S. Again, hard to project onto because you'd be solving hard problems in computer science if you could. And the number of samples you need to obtain a risk 1 estimate, if in fact you could project onto this, is this number. Based on the realization that M is a very sparse matrix and consequently every element of the signal set is also very sparse, you could use a scale L1 ball as a set to project onto, a suitably scaled L1 ball. And this has runtime much, much smaller than this and differs by just a constant factor. It's a larger constant in terms of the number of samples required for risk 1. A third example is one where the signal set S, this is I think interesting for other reasons, beyond just inference, I suppose, is where the signal set S consists of perfect matchings, the set of all perfect matchings in a complete graph. And this shows up in certain problems in network inference, actually. The complete graph is just the graph consisting of every node connected to every other. A matching in a graph, a matching of a graph is a subset of edges where every node is incident to at most one edge. And a perfect matching is a subset of edges where every node is incident to exactly one In this case, the best possible convex estimator that you can write down involves using the convex color-best, which is in fact polytime computable, using some very beautiful ideas from Mayfair. Polytime, but a very large poly. Okay? There's a very nice relaxation of this set that's very, very easy to project onto based on just sorting, essentially. That's why you get things that look like this. And that again differs by just a constant terms of the number of samples you need for a risk one. So the point in just making this, the point in having this example here, is that it's not just the case that we want to go from super polynomial to polynomial, but we also care about going from polynomial to less polynomial as we get more and more data. Yeah?
Do you know the exact value of the constant C1?
In this case, it's 1, 2, and 6. In this case, I don't know. I can prove that it's larger. In this case, I can prove that it's larger. This one case, I've really, really tried to understand. But in general, other than proving that it's larger, I'm not able to see.
Do you know of any example that n change the order?
Yep. That's the next one. Yeah. And so, there's a fourth example where the number of samples is qualitatively, I mean, it's larger beyond just a constant factor. And this is motivated by problems in sparse PCA and actually more closely related to some problems involving gene expression patterns and so on, where the signal set S consists of adjacency matrices of small cliques in a big graph, where the clique is planted on square root of the nodes of the graph. Square root is a nice number of various reasons. In this case, projecting onto the convex hull of S is again hard. But if you could, the number of samples required for your risk-1 estimate is something like the 4th root of P. Again, by realizing that the signal set S consists of rank 1 matrices, effectively, using a nuclear norm-based approximation, which requires basically an SVD computation, a projection. It's much simpler computationally, but requires square root P samples. So this is an example where you do need more than just a constant factor more data to get to a much simpler. And tried hard to find something in between. Doesn't mean there doesn't exist one, but and this will also have implications for the planted clique problem and other sorts. So one simple point. In this last example, I had the convex hull of S, which was hard, the nuclear norm ball. What if we use an even weaker relaxation than a nuclear norm ball? Like a Euclidean ball. Why did I not have a third line in this table?
Then you can't achieve the same level of risk.
Well, I mean, assume I give you more data, right? I mean, so I give you more data. Sure, I'm using a weaker algorithm, so it would require more data to get to the same risk. So that's certainly true.
Trade up with the sample.
Yeah, and that's exactly the point, which is, if I in fact use a properly scaled Euclidean ball, projecting onto that set is very easy, but the number of samples I need to be able to produce a risk-1 estimate goes from order square root P to order P. Now if you have order P samples, the number of operations to compute the sample mean is itself order P squared, and this is the number of operations to project onto the Euclidean ball. That's just order P, right? And so you end up with something that's order P squared computation. You're using a very simple post-aggregation algorithm. The projection is very simple, but the amount of data that you need to even be able to use such a simple algorithm is so large that sort of the pre-processing step requires a lot of computation. So in this sense, if you're going to decide between using the nuclear norm procedure versus the Euclidean projection procedure, and I give you order P samples, what you should do if your decision is just between these two procedures in this computational framework, so it's a very restricted statement, it's between these two procedures under this model of computation, what you should do is throw away all the excess data beyond order square root p and use the slightly more complex procedure because it is actually computationally beneficial for you. Okay. So in this case, in this very restricted way of thinking about things, it actually makes sense to throw away excess data. And this goes back to the sort of kink that we talked about right at the beginning. Right? I mean, there are several caveats. To actually be able to state this result formally as a theorem, what you do need are computational lower bounds. And I'm not actually talking about computational lower bounds. It depends on the computational architecture. You know, some might point out that computing the sample mean is easily parallelizable, whereas computing subsequent projections may not be. And so the way you account for this could actually be different from the way you account for the projection. And if you do these different kinds of accounting, you know, these kinks would occur at different times.
So for instance, in this case, you can, you know, before doing SVD, sparsify and then use power method for, and you should go below the p to the 3 halves. Right?
Yeah. I mean, that's.
So this is only if you do the power method.
Yeah, if I use just the SVD. Yeah.
SVD
Without doing. Yeah. Exactly. So that's So I mean, I'm using a particular procedure to solve that. Absolutely.
But this suggests that you don't have a computational lower bound.
Yeah, I mean, I'm not saying computational lower bound. I'm just saying within the limited space of algorithms that I allow myself to consider, at some point it makes sense to throw away data and use the same algorithm. I'm not saying that this is a lower bound. The lower bound might be somewhere here. I'm not saying I achieved that lower bound. Okay. So I think there are some questions raised by some of these examples. And several of the examples, as was pointed out, you don't need too much extra data, just a constant factor more data, to be able to back off to really simple algorithms. And this, if you're familiar with, these convex relaxations, is in fact a bit of a surprise. A lot of the convex relaxations that I used, a computer scientist would call them really, really weak. Really bad convex relaxations to use. The reason is the sense in which they measure quality of approximation, or quality of a relaxation, is via a quantity called the approximation ratio. So if I have this convex set, and if I have that outer relaxation to it, the way quality of approximation is measured in computer science or in theoretical CS, where the goal is to solve a combinatorial optimization problem typically, is to look in all directions and look at, roughly speaking, what the gap is between your convex set and what the relaxation is. And this is really the sense in which you care about quality of approximation if your goal is combinatorial optimization. But if your goal is denoising or statistical inference in the sense that I've just described, what you care about is how these Gaussian complexities of these fattened cones look like. And these may well be benign. The ratio of these guys may be constant independent of dimension, as many of these examples say, while this ratio may actually be growing in a bad way with dimension. So the sense,
Well, there's one difference here that you didn't mention. Maybe you're just about to, but at the core of the feasible cone viewpoint is that you're at a special point.
Yeah.
And at the core of the CS view about approximation ratio is you're looking over all points and you want a guarantee that's good no matter what's thrown at you.
True.
Right? So that there's...
So I think there are two things here. One is the fact that I care about these boundaries, whereas they look in all directions, and I average, whereas they look at worst case. So I mean, there are two facts here, absolutely. But yeah, both of them together are buying you something here, which is that there are computationally very tractable relaxations that are actually very sensible to use in this context that perhaps may not be sensible to use in combinatorial. So just to conclude, I talked about some of these challenges with massive data sets. And considered a simple denoising problem to describe these challenges more concretely. And one can obtain these sorts of time-data trade-offs in these denoising problems by using convex relaxation as an algorithm weakening mechanism. And that is, I think, very essential to realizing these sorts of time-data trade-offs. I think there's a lot of interesting potential questions in future work. One is to consider how these Gaussian complexities change as I look at hierarchies of LP or STP relaxations. So a sort of canonical question, if you will, in the theoretical computer science literature is to say, how do approximation ratios change as I go up and down these hierarchies of LP or STP relaxation? How do Gaussian complexities change as opposed to approximation ratios as I look at these hierarchies? I think that's an interesting question because the answer appears that they'll be qualitatively different. Other potential methods to weaken algorithms beyond convex relaxation, one can imagine things like dimensionality reduction, where you project, as you get more and more data, project it onto lower and lower dimensional spaces and maybe do processing in some low dimensional space. Clustering, other sorts of ideas being relevant. And I think most importantly also, especially in a massive data context, is to look at heterogeneous data. You don't expect massive data to be homogeneous. Every data point will look the same somehow. I looked at the sort of IID data setting where all data points are basically drawn from the same distribution, same source. So you do care about non-stationary sources and heterogeneity in data. A paper describing all these ideas is on the website. Thank you.
So if you do the relaxation using two different speeds, one is bigger, one is smaller, how do you guarantee that you get the same result?
What do you mean one is bigger?
Like you're saying if you make the cone bigger, it's better.
It's better computationally.
It's better computational. So my question is, how do you make sure that the results that you're getting are the same?
Well, the results are not the same. Just the quality of the result is the same, given access to more data. So given access to more data, I'm going to use a weaker convex relaxation. And
But you're not solving the same problem, right?
I'm not solving the same problem. Well, I care about the same objective, and with respect to that objective, I'm going to produce a solution that's just the same quality. But yeah, the solutions don't necessarily need to match up, but the mean squared error will be the same. Will be one.
So what is the low-hanging fruit here of an example where someone needs this and it's the first thing they ought to do? Like what is of all that you listed lots of different potential relaxations and problems, what do you consider the best to be trying?
I think
I
think sparse PCA is a very nice example potentially.
Mm-hmm.
It's an example where the noise, for natural reasons, is better modeled as Wishart rather than Gaussian in the sense that I've described here. But modulo that which affects, I guess, the statistical analysis. Considering these sorts of STP relaxations between the nuclear norm and this sort of intractable one. There are much tighter relaxations you could actually write down. They're much tighter than the nuclear norm with the convex hollow-S. And I think in this case, where you have rank 1 matrices that are also very sparse, constructing good relaxations to that convex is, I think, something that in terms of low-hanging fruit, I don't have a proposal for a relaxation to use, but I think.
So could we just discuss this specific one? So when you say on the square root of the nodes, that's a feature you injected into the problem. In a real version of this, it would be a parameter.
Yeah.
That there would be the largest clique that you're willing to consider might be present in some gene set.
Yeah.
Right? And then all these exponents would change based on the size of the clique and so on. So
not quite. I mean, this relaxation does not depend on the fact that this square root is. I mean, this potentially is what changes. But the runtime does not change. Because these relaxations actually don't depend on the specific sign. But, I mean, there was a low-hanging fruit. I don't have a proposal, like I mentioned, that suggests something between these. And I think that's an interesting question.
I don't think it's a long-hanging fruit.
It's an interesting question. Yeah.
So, is there any hope here to get an alter the lower bound?
There's interesting work on lower bounds and convex optimization, but even there, you sort of need to restrict yourself to a particular family of algorithms. I think one of the most powerful ways to produce lower bounds in general that we know of is Fanow's inequality. And so there's work actually by Alec Agarwal and Martin Wainwright on converting certain classes of stochastic convex optimization problems to certain estimation problems, and then applying Fanow's inequality to get sort of information, translating these information theoretic lower bounds to sort of reasonable computational lower bounds. But again, operating under a very specific computational assumption. But I just think we don't have very good ways to produce lower bounds computationally, other than to say the number of operations should be larger than the size of your input. That's effectively what we say for the satisfiability problem and so on. But I mean, the most interesting techniques I've seen actually rely on Fanow's inequality, which is something completely different.
Can you relax the Gaussianity assumption?
Yes, in the sense that, I mean, if you use this estimator still, just project in the least square sense to disencombinate set, then you just have to change his expectation was still with respect to your noise, but rather than Gaussian complexity, it'd be whatever other complexity. So that doesn't change. It's just that, if you have non-Gaussian noise, you may actually prefer to use a different estimator. But if you use this estimator, this is what you do.
Yes, but then would it still correspond somehow?
Oh no, all the scalings that I described, all the sample complexity.
I don't think you ever need to get away from Gaussian complexity. I mean, that's the central message of all of modern statistics. You just do your aggregation by medians or robust estimator, and then you use your projection linear and the noise, and once you've done your nonlinear
the aggregation,
that's trivial, no problem. I mean, it would be really, really hard to think of something where you couldn't beat the non-Gaussian. If it's really IID noise or something like that, you can beat the